Multi-priced timed automata extend classical finite-state automata with real-valued variables, called clocks, that evolve with derivative 1 and can be queried and reset along transitions. Additionally, they feature write-only variables, called observers, with non-negative slopes that can change from one location to another, modeling the accumulation of costs or resources along a computation. Unlike clocks, observers may not be queried while taking edges, placing multi-priced timed automata between timed automata, where reachability is decidable, and linear hybrid automata, where reachability is undecidable. A natural class of verification problems for multi-priced timed automata involves reachability subject to constraints on the observers, such as the domination problem, which asks to reach a location subject to upper bounds on each observer. Previous work considered observers with non-negative slopes in every location. This paper treats observers with both positive and negative rates, introducing a new level of complexity. The main result is an algorithm to decide a gap version of the reachability problem for this variant of multi-priced timed automata. The gap reachability problem is translated into a gap satisfiability problem for mixed integer systems of nonlinear constraints, which is then solved via a combination of branch and bound and relaxation and rounding. The main technical contribution is a procedure to solve such constraints, involving bilinear constraints, existential theory of real closed fields, Diophantine approximation, and Pareto curves. This novel approach combines theoretical computer science and mathematical concepts to tackle the reachability problem for multi-priced timed automata with positive and negative rates, providing a significant advancement in the field. The paper explores the decidability of the gap domination problem for multi-priced timed automata, MPTA, with both positive and negative rates. The gap domination problem is a variant of the domination problem, which partitions observers into cost variables and reward variables and asks to reach a location subject to upper bounds on costs and lower bounds on rewards. While the domination problem is undecidable, the gap domination problem is decidable, implying that the Pareto curve of undominated reachable cost vectors can be computed to arbitrary precision. The main result of the paper is to establish decidability, in non-deterministic exponential time, of the gap domination problem in the presence of positive and negative rates via a new decision procedure. This procedure involves a combination of relaxation and rounding and branch and bound, relying on Khinchin's flatness theorem from Diophantine approximation. The authors formulate a relaxation of the system of constraints such that a solution to the relaxed version can be rounded to a solution of the original problem, while unsolvability of the relaxed version permits a branch and bound step that eliminates a variable from the original system of constraints. This work is of independent interest, as systems of nonlinear constraints over integer and real variables appear in many different domains. The author's method is novel, as previous work has not addressed the gap problem for MPTA with positive and negative rates. The paper builds upon previous results on MPTA with a single observer, where the optimal cost to reach a given location is computable. However, the present paper considers MPTA with arbitrarily many observers, relying on the simplex automaton abstraction introduced in previous work. Overall, the paper's main contribution is the decidability of the gap domination problem for MPTA with positive and negative rates, achieved through a novel decision procedure that combines relaxation and rounding and branch and bound techniques. Multi-priced timed automata, MPTA, is a concept that combines the principles of timed automata with cost information, providing a framework for modeling and analyzing systems involving both time and cost aspects. An MPTA is defined as a tuple consisting of a set of locations, an initial location, accepting locations, clock variables, observers, edges, and a rate function. The value of a run in an MPTA is calculated based on the time spent in each location and the corresponding rate of the observers. The domination problem, introduced in this section, involves deciding whether there exists an accepting run in an MPTA such that the value of the run is less than or equal to a given target vector. This problem can be reformulated to include more general linear constraints by introducing fresh observers. The domination problem is PSPACE complete for MPTA with positive rates only, but it becomes undecidable when negative rates are allowed. To address these limitations, the authors introduce the gap domination problem, a variant of the domination problem. The provided example in Figure 1 illustrates the operational semantics of an MPTA, demonstrating how clock valuations and observer rates evolve over time. This paper's focus on MPTA and the domination problem highlights the importance of understanding the behavior of complex systems involving both time and cost aspects, which are crucial in various applications such as scheduling, resource allocation, and real-time systems. Multi-priced timed automata, or MTPAs, are timed automata with multiple clocks and observer variables that aggregate the total dwell time in different states. An example of an MTPA with 3 clocks and 2 observer variables is illustrated in Figure 1. A run of the MTPA is determined by a sequence of non-negative real numbers, giving the delays between successive transitions. The accepting run is subject to 2 objectives. The observer variable E, representing even states, must be at least 2, and the observer variable O, representing odd states, must be at least 1. In pure reachability objectives, there is an explicit upper bound on the granularity of the delays in a run witnessing that the objective is realizable. However, this no longer holds when reachability objectives contain both upper and lower bounds on observers. The gap domination problem is a decision problem that takes an MTPA, evaluation gamma, and a slack parameter epsilon greater than 0 as input. It asks whether there exists a run rho such that the valuation of rho is less than or equal to gamma minus epsilon. If such a run exists, the output is dominated, and if no such run exists, the output is not dominated. A key result is that the set of reachable observer vectors consists of a countable union of simplexes, where each simplex is specified by its vertices, a tuple of integer vectors. This allows us to reduce the gap domination problem to a Diophantine problem. The proof involves constructing a new MPTA, with non-negative rates, and the general case follows from the proof in 12. The authors delve into the analysis of mixed-integer bilinear (MIB) systems, which consist of constraints involving integer variables x and real variables y. These constraints include bilinear equations of the form x_ta_i less than equals b_i, where a_i is a matrix, x is an integer vector, y is a real vector, and b_i is a constant. Additionally, there are linear constraints cx less than equals d and ey less than equals f, where c and e are matrices, and d and f are vectors. All constants in the system are assumed to be integer, implying that if the system is satisfiable, there exists a satisfying assignment with y as a rational vector. The concept of slack epsilon is introduced, referring to a satisfying assignment where x_ta_iy less than equals b_i epsilon for all I. A system is considered bounded if the polyhedron y element of R_n ey less than equals f is bounded, i.e., it is a polytope. Notably, the MIB systems derived from multi-priced timed automata in Corollary 2 are bounded. However, the authors also prove that the satisfiability problem for bounded MIB systems is undecidable. This result is established through a reduction from Hilbert's 10th problem, a well-known undecidable problem in mathematics. The reduction involves transforming the given system S into an equisatisfiable MIB system S, which includes a new variable x_0 and additional constraints. This transformation ensures that S and S are equisatisfiable, meaning they have solutions simultaneously. The author's work highlights the complexity and challenges associated with solving MIB systems, even when they are bounded. This underscores the importance of developing efficient approximation algorithms or heuristics to tackle such problems in practice. Researchers construct a system S that extends a given system S of multi-priced timed automata with positive and negative rates and real variables y1, yn is greater than or equal to 0. This construction ensures that every solution of S extends to a solution of S, and, conversely, every solution of S restricts to a solution of S. System S includes equations x0 equals 1 and xi equals 1 for I equals 1, n, as well as linear equations xi equals xj plus xk from S and equations xj plus xk, y equals x0, yj plus yk, for each equation xi equals xj xk in S. The authors then introduce the gap satisfiability problem for multi-input Bucci (MIB) systems, which seeks a procedure that inputs epsilon greater than 0 in a MIB system S in a specific form and returns either unsat or SAT, subject to certain requirements. Notably, the gap satisfiability problem is decidable for bounded MIB systems, but the authors demonstrate that it is undecidable for unbounded MIB systems. The proof of undecidability is achieved by reduction from Hilbert's 10th problem, which involves a system of equations in positive integer variables x1, xn. Given such a system, the authors construct an MIB system S, such that every satisfying assignment of S extends to a satisfying assignment of S, with slack 1/2, and every satisfying assignment of S restricts to a satisfying assignment of S. This construction involves adding equations and inequalities to S that force xi and yi to be very close together, thereby establishing the undecidability of the gap satisfiability problem for unbounded MIB systems. The decidability of the MIB problem in the bounded case is examined, introducing key concepts and tools for analysis. A subclass of MIB systems, called positive MIB systems, can be solved using a naive relaxing and rounding procedure without requiring boundedness. However, this variant is insufficient for handling MPTA with both positive and negative rates. Two crucial propositions are presented: Proposition 5, concerning semilinear sets of integers, and Proposition 6, dealing with semi-algebraic sets of real numbers. These propositions are instrumental in the subsequent analysis. To analyze the MIB problem, the authors transform it to a standard form, as shown in equation 3. This transformation involves enriching nonlinear constraints to include an extra linear term in Y and ensuring only non-negative linear constraints on integer variables. The transformation is based on writing the set S as a semilinear set L, B, P, following proposition 5, where B is a subset of Zm and P is an MBYD integer matrix, with D being the dimension of the affine hull of S. For each vector W in B, the authors apply the change of variables x equals pz plus w to the original system, 2, resulting in a problem in standard form. This process yields a finite collection of problems in standard form, whose solutions are in 1:1 correspondence with the solutions of the original system, 2. Researchers introduce a relaxed version of a bounded multi-integer bilinear system, where variables range over the reals. This relaxation enables rounding an assignment to the relaxed problem into an integer solution of the original system or leads to a branch and bound step, resulting in an equisatisfiable finite collection of MIB instances with one fewer integer variable. The rounding process leverages the flatness theorem in Diophantine approximation, which states that every convex polyhedron K with width K greater than omega n contains an integer point. The flatness constant omega n depends solely on n, with the best known upper bound being O n^3/2, although a linear upper bound has been conjectured. The authors also discuss the definability of lattice width for classes of polyhedral sets, demonstrating that there exists a quantifier-free formula in the theory of real closed fields that expresses the property width U, P, is greater than or equal to C, where P is a non-empty polyhedron defined by a matrix A, vector B, and scalar C greater than 0. The relaxation construction begins with a bounded MIB program in standard form and a slack epsilon greater than 0. The system admits a solution X element of Z(m) if and only if the polyhedral set P, Y, contains an integer point, where P, Y, is defined as a set of X element of R(m) satisfying constraints based on A, B, and C. In the context of system 3, let H be an upper bound for the absolute value of integer constants. Given that S is bounded by 14, lemma 3.1.25, the set Y element of Rn die is less than or equal to E is contained within a ball of radius kappa 1 centered at the origin, where kappa 1 equals m1/2 H, m2 plus m. For a matrix A, let parallel denote the spectral norm. It is recalled that if A has entries of absolute value at most H and has m columns, then parallel is less than or equal to square root mh. Define delta equals min delta 0, 1, where delta 0 equals min epsilon parallel kappa 1. I equals 1, L is greater than or equal to epsilon, m1 half h kappa 1. Define U equals U element of Zm, 0, 2 delta parallel U parallel less than omega, m, where omega, m, is as in theorem 7. Write U equals U1, S, and consider the relaxed system S of linear and bilinear constraints in exclusively real variables. Proposition 9 states that if the relaxed system S is satisfiable, then so is the original system S. The proof involves considering a solution X, Y of the system S, and showing that the ball B delta, X, is contained in P, Y, which implies that width U, P, Y, is greater than or equal to omega, M. For all U in U hence, by theorem 7, P, Y, contains an integer point, making the original system S satisfiable. Proposition 10 states that if the relaxed system S has no solution, then every solution X element of Zm of the original system S that has slack epsilon either has some component equal to 0 or satisfies Ux is less than or equal to kappa 2 for some U element of U, where kappa 2 is an explicit constant depending only on S and epsilon. The proof involves showing that if X, Y is a solution of S with slack epsilon, then either some component of X is 0 or Ux is less than or equal to omega, M, for some U element of U, which leads to the desired bound. For multi-priced timed automata with positive and negative rates, the authors investigate reachability by considering a scenario where the polytope P, Y, does not contain the origin. Through geometric reasoning, they derive an upper bound on the magnitude of X, denoted as kappa 2, in terms of M, epsilon, and other system parameters. The authors then develop a decision procedure for the gap satisfiability problem in bounded MIB systems, which leverages the relaxation construction presented earlier. This procedure involves constructing the associated relaxed system S, determining its satisfiability using a decision procedure for the existential theory of real closed fields, and then enumerating through all possible integer points within the polytope P, Y, to find a satisfying assignment of the original MIB system S. This novel approach enables the efficient solution of the gap satisfiability problem, which is crucial in verifying the correctness of MIB systems. The derived upper bound kappa 2 provides a critical insight into the relationship between system parameters and reachability, while the decision procedure offers a practical method for identifying satisfying assignments in complex MIB systems. In the context of mixed integer bilevel MIB systems, the variable elimination process is crucial for bounding the size of integer variables involved. A single variable elimination step can be analyzed by asserting a linear equation U(Tx equals b), where U and b are bounded by kappa_3, a function of m, h, and epsilon. Applying proposition 5, we obtain a substitution x equals pz plus w, with the elements of p and w having absolute values bounded by kappa_3. Since there are m integer variables, the constants appearing over all MIB instances through the process of variable elimination have absolute values at most kappa_3 m squared. The paper also considers a version of the relaxed system, 6, with integer constants having magnitude at most kappa_3 m squared. To enhance the complexity analysis, the system is augmented with a new variable r and constraints r is greater than or equal to x plus 1 and r is greater than or equal to w plus or minus w m u for each vertex w of the polyhedron P, Y, and U element of U. The integer constants in the resulting system have absolute values at most kappa_3 m cubed, due to Hadamard's determinant inequality. By construction, if x caret, y caret is a satisfying assignment of 6, the convex set x element of P, y caret x is less than or equal to r, has lattice width at most w, m, and hence contains an integer point. By proposition 6, an upper bound for r is 2 kappa_3 m cubed plus mn, which concludes the proof of theorem 12. Notably, the double exponential dependence of the magnitude of the smallest satisfying assignment on the number of variables in theorem 12 is unavoidable, as stated in remark 13. This refined version maintains the technical accuracy and depth of the original content while providing a concise and clear explanation suitable for voiceover narration. This paper introduces a novel approach to analyzing multi-priced timed automata, MPTA, with both positive and negative rates. The authors propose the concept of the Pareto curve, which represents the set of undominated reachable observer values in an MPTA. They demonstrate how this curve can be approximated to arbitrary precision using a reduction to the gap satisfiability problem for bounded mixed-integer linear systems. MPTA and their associated observer values are defined, highlighting that the reachability problem for such systems is undecidable due to the presence of negative rates. However, the Pareto curve can be computed approximately using a non-deterministic exponential time Turing reduction of the gap domination problem for MPTA to the gap satisfiability problem for bounded mixed-integer linear systems. The implications of these results on weighted timed games are discussed, noting that unlike MPTA, the optimal value of a weighted timed game with positive and negative rates cannot be computed to arbitrary precision. Additionally, for any MPTA with guards comprising both strict and non-strict inequalities, there exists an MPTA with exclusively closed guards over the same set of observers, such that every observer valuation reachable in A is also reachable in A, and vice versa. Future work involves considering the feasibility of approximate Pareto analysis over infinite runs of MPTA. For double-priced timed automata, computing the optimal reward-to-cost ratio over infinite computations is possible using the corner point abstraction. For more general MPTA, specifications referring to multiple reward-to-cost ratios are a natural extension. I'm happy to help. However, it seems like there is no content provided for me to refine. Please provide the transcript or research paper you'd like me to refine, and I'll be happy to assist you in creating a concise, technically accurate summary suitable for voiceover narration. The authors extend their Pareto optimal reachability analysis for simple-priced timed automata to multi-priced timed automata with positive and negative rates, enabling the modeling of complex systems with both types of rates. The reachability problem is defined as a decision problem, where the goal is to determine whether a target location is reachable from an initial location while satisfying constraints on accumulated costs. The authors propose an algorithm to solve this problem, involving iterative computation of reachable states and corresponding accumulated costs. This algorithm is based on computing reachability witnesses, sequences of transitions leading to the target location while satisfying cost constraints. These witnesses are computed using a modified region graph construction that accounts for positive and negative rates. The algorithm's complexity is polynomial in the input automaton's size, but its precision and computational complexity require careful parameter tuning. The authors compare their approach to existing reachability analysis methods, highlighting its ability to handle both positive and negative rates. However, they also acknowledge limitations, including the assumption of a finite number of locations and the need for further research on scalability to larger systems. This approach has potential applications in real-time, embedded, and cyber-physical systems, where modeling and analyzing complex systems with both positive and negative rates is crucial.